Hello, my name's Andrew Katz, and today we'll be talking about open hardware. The topics that I'll be covering are, first of all, what is open hardware? How is open hardware licensed? All about open silicon in context, how open silicon is being developed and is being exploited and is being very successful internationally, and also then I'm going to talk about the European Commission study which I was involved with and which was published last year. So let's start with what is open hardware. Well, open hardware is hardware, the design for which is publicly available. And like open source software, it can be used, it can be freely made or built or manufactured, it can be freely studied, it can be modified, it can be copied, and then once it's been copied, it's possible to provide those modifications, the designs, etc., to other people. And that includes by selling the modified designs or the modified hardware. And this is all without restriction, except for some restrictions relating to attribution and reciprocity, which we will talk about later. So the definition of open hardware, well, the best place to look is probably the Open Source Hardware Association, and the URL for them is just there. It's based on the open source definition, and that was drafted by Bruce Perens, and originally he developed it for the Debian project, but then subsequently when he co-founded the Open Source Initiative, he adopted most of the Debian free software guidelines and turned them into the open source definition. So what's the distinction between open hardware and open source hardware? Well, the reality is not a lot. The terms are generally used pretty interchangeably, so I wouldn't worry too much about the distinction between the two. So when we're talking about hardware, exactly what do we mean by that? Well, it can include things like cars. A while ago I was involved in a project called the River Simple Hirban car, which is a car which is powered by hydrogen. It can be electronics. So for example, many of you will be aware of a project called Arduino. They make a range of small microcontroller boards, and those are all available as open source hardware. There are also medical devices. So one of many examples of this is something called the U-Visor, and I've put the URL for that down there. And the growth in open hardware for medical purposes has been grown significantly as a result of COVID, perhaps not surprisingly. It could even be fluid. So, for example, someone, partially as a joke, released the idea of open cola. So that's an open source cola drink, which is designed to be as close to Coca-Cola as possible. And then 3D printers themselves can be open hardware. RepRap is a particularly interesting example because it's a 3D printer, the designs for which are available as open hardware. And it can also be used essentially to print itself, or at least a large proportion of the components of the RepRap can themselves be printed on another RepRap. Perhaps most interestingly at the moment, it can also cover silicon. And by this we mean things like processor chips and cores. So two very prominent examples of that are Sci5, and they've produced a number of cores called the Freedom cores, and that's derived out of the RISC-V architecture, which is an instruction set architecture which is itself available under an open source license. And I've given you an URL for that there. So, how is open hardware licensed? Well, many people use open source software licenses for licensing open hardware. So, classic examples of those would be Apache 2.0 or the BSD software licenses. Both of those are very permissive licenses. And then GPL, which is a reciprocal software license. They can also be licensed using Creative Commons licenses, so CC0, which is a public domain dedication and license, and CC BY, which is an attribution license. CC BY SA is also an attribution license, but this is a share-alike license, which means that if you license a design under it and you make modifications and then you redistribute that design, then you need to make sure that that design, including all of its modifications, are released under the same license. There are also dedicated open hardware licenses, and I was involved in drafting two of them. One of them is the CERN Open Hardware license, which comes in 3 different flavors. So that's strong reciprocal, weak reciprocal, and permissive. And then there is the solderpad license, which is purely permissive license, and it's very closely based on the Apache software license. Another reciprocal license is the TAPR license, which uses patents as a mechanism for ensuring the reciprocity. So the challenges that we have in licensing open hardware are, first of all, that hardware is in many ways very different from software. So that means that different types of intellectual property are likely to apply. For reciprocal licenses, and sometimes people call them copyleft or share-alike licenses, a fundamental question is, where does the boundary lie? So what that means is that if you are releasing a design under one of these licenses, and for example, it's for an electronic circuit, that electronic circuit is likely to contain components, and the question is, do you need to provide the recipes or the designs for making all of those components? And this is an issue that the reciprocal open hardware licenses have been trying to deal with. Another question is, what is the corresponding source? And this is a term that's used in open source software. The corresponding source code is a source code that you need to be able to modify or reproduce the software. So what do we mean by that in hardware? Well, it's normally, when we're talking about source code, we're mapping that onto hardware, we're talking about the designs. But the question is, what do those designs mean? Are they CAD drawings, or are they configurations of processors, for example, in something like VHDL? Do they even have to be digital at all, or can they be just instructions, a recipe for how to make something, and so on? So it's much more complicated to determine what source code means in the context of hardware than it does in software. And what is the next question is, how can you make the reciprocity stick when transferring a physical article? So what this means is that if we look at open source software, for example, whenever you transfer a piece of code, there's a very high probability that you're going to be copying that code as part of the process. And during the copying process, you're going to need some sort of license to permit that copying, and that license is an opportunity to apply something like the GPL, so it's an opportunity to apply the obligation to make sure that that design is relicensed under the same license. So every time, virtually anything you do with software is going to involve some sort of copying or reproduction or distribution. These are all things that are controlled by copyright law. When you have something controlled by copyright law, you have the ability to apply a license, and if you have the ability to apply a license, you have ability to apply conditions like the conditions that are contained within the GPL. It's much more difficult to do that with certain types of hardware. So, for example, if I create a hammer or a screwdriver, for example, and then I pass the physical item on to somebody else, does that mean that they also would have the right under an open source hardware license to receive the designs for that hammer or that screwdriver? And the answer to that in many cases is no, they don't. So it makes it much more difficult for these obligations to ensure that any recipient of the open hardware item has got access to the designs themselves. And the various licenses do have mechanisms that try to address that, but it is a fundamental problem related to the way that different legal systems and different sorts of intellectual property work, and it makes that significantly more difficult. One aspect that is quite interesting, however, is that some hardware is much more like software, and an example of that is open silicon. So let's talk about open silicon. So hard hardware is different from software. And what do I mean by hard hardware? Well, I mean physical items like an open source car or an open source dump truck, or even things like electronics built using a circuit board. So, for example, what you will typically need is you'll need some sort of physical material to make that sort of hardware. Obviously, with a car or a dump truck, you'll need a lot of steel, you'll need rubber to make the tires, you'll need a whole load of plastics, and so on. You'll need a physical space as well, so you'll need some sort of factory or a workshop or a laboratory And that itself may need to have certain environmental considerations as well. So it may simply be that it needs to be enclosed from the elements. It may need to have a certain temperature. And if you're talking about certain types of hardware, you may be looking at very specific constraints like lack of vibration or the quality of the air or a lack of dust and so on. And one of the aspects of hardware is that it's generally more difficult to copy than a piece of software. And by copying, I mean simply, if you wanted to take the Linux kernel and copy that, then all you do is just type a command into your computer and it immediately copies it binary bit by bit, and you get a perfect copy for virtually zero cost in just a number of milliseconds. Clearly, if you have a dump truck, then being able to copy the dump truck is something that is sort of dramatically more complex than just being able to copy a piece of software. It's also much more difficult to transport hardware than it is to transport software. So software you can you can transport software very simply over the internet just by downloading it, but any piece of hardware, because it's physical, is going to require some sort of requirement for transport. And quite often it's more difficult to test and configure hardware than it is for software as well. Because software, if it's in an identical environment to previous copies of that software, will react in exactly the same way, and the setting up and configuration will be exactly the same. Even if you provide a piece of hardware with an identical environment, there will always be slight variations in the tolerances of the components that you're using, or the way that it interacts with the environment, and so on. So that's likely to be slightly more complicated. So those are some distinctions. Whereas, in contrast, open silicon is much more like software in many ways. So what is open silicon? Well, we're talking about the code that is written to define a set of logic and other components in a chip. And it could be a processor, it could be a memory chip, it could be various different sorts of interface, for example. And these configuration files, which are written in a language which looks very like software, are going to be released as an open hardware file. So VHDL is the hardware description languages, for example, looks very much like software code, and it's developed in a very similar way. So the same sort of collaborative tools that you can use when you're developing open source software, you can use when you're developing open silicon as well. And many of them will be very familiar already to software developers and authors. So, for example, you can store your open hardware code in locations like GitLab and GitHub using version management systems like Git. And all of the collaboration that you can use with open source software can also be used in the same context with open source hardware. And in the same way that with open source software, there are many tools available to compile the code, link the code, and also test it and run it. In the same way, there are many tools available purely in software that will enable you to test and simulate your open hardware designs without going anywhere near anything physical. Everything can happen inside a computer. And even if you do want, when you've done that, to turn your open hardware, open silicon designs into something that works in the real world, then the target may be a chip called an Fpga. So what is an Fpga? Well, Fpga stands for a field programmable gate array, and it's essentially a component that contains a large number of blank gates and other electronic components which can be configured by the code that you're putting together. Now, I'm avoiding using the word programmable, although that's what a lot of Fpga designers and users will describe it, because I think there's a subtle difference between programming, which is probably something that is better used in the context of software, and configuring. Because when you've configured your Fpga, you do end up essentially with a chip that has its own characteristics. It becomes the characteristics of the open silicon configuration files that you're feeding into it. And the way it's configured is by using something called a bit stream. So once you have written your configuration in some form of hardware description language, and then you've processed that through your open hardware toolchain, then you will end up with something called a bit stream, which is literally just a stream of bits which is fed into the FPGA. And once the FPGA has ingested that bit stream, it becomes configured in a way that means that it essentially becomes the component, the processor, or whatever that you have configured it to be. So the tool chain, which is used to create and write the hardware description language, is called an EDA tool. That's Electronic Design Automation Tool. And once you have developed your chip design in an FPGA, you can also use those tools to create configuration files which can then be sent to a chip foundry to develop something called an ASIC, the Application-Specific Integrated Circuit. And essentially an ASIC is any chip that isn't an FPGA. And the advantage of ASICs is that they can be produced in extremely high volume and extremely low cost, but the disadvantage is that the setup costs for producing an ASIC are pretty high to begin with. So once you've paid those setup costs, and once you have your foundry configured to produce your chips, then the per item, per unit cost of each individual chip becomes much, much lower. So let's talk about open silicon in context. You can't really talk about open silicon without talking about RISC-V. And RISC-V is an instruction set architecture, and it was released by the University of California at Berkeley. Now, an instruction set architecture is essentially a list of all of the codes that you use in order to configure and program a processor chip to run a particular piece of software. And what it does is producing the standard RISC-V instruction set architecture enables people to produce chips which may all operate very differently internally, but ultimately it means that because they're using the same instruction set architecture, it becomes much easier to transfer a program which has been written for one RISC-V based chip to another RISC-V based chip. And that means that there are a number of RISC-V compatible cores which have been made available in open silicon, and there's also a large number that have been made available under proprietary license as well. And some examples of these are as follows. So Sci5 has produced a number of what they call freedom cores, and they are all released under the permissive BSD license. Western Digital have used the Apache license to release their Swerve core. An organisation in the UK called Low Risk has produced cores called OpenTitan, and they're available under also the Apache license. And the Open Hardware Group has produced Core 5, which is released under the SolderPad license, and that is yet another permissive open hardware license. So let's now talk about the impact of open silicon internationally. So if we look specifically at China, we can see that of the 20 premier members of RISC-V International, half of them are Chinese, and that includes organizations as well known as Huawei Technologies and also Alibaba Cloud, but there are many others obviously as well. It's also worth noting that organizations like UNISOC and ZTE and the Institute of Computing Technology are also members of the RISC-V Foundation as well. Turning to India, India has done a lot of development around its own custom RISC-V cores, which are called Shakti and Vega. And in Europe, we have a fair amount of activity as well. Members of the RISC-V Foundation include Low Risk, that I mentioned before, Pulp, and Arduino. And there are a number of active RISC-V groups throughout the world. So in the Asia-Pacific region, there are 12. In North America, there are 7. And in Europe, the Middle East, and Africa, there are 6. And these are all, throughout the world, a number of active organizations who are all participating in RISC-V and providing a group forums to enable discussion and development of various aspects of RISC-V and compatible cores. So let's look at the economic effect and the impact of RISC-V. So I mentioned Sci-5 before. Sci-5 is a company which is founded by a number of members of the RISC-V team, and currently, or at least recently, it has had a valuation of $2.5 billion, which is 16 billion yuan. So it's clearly a very significant and large organization. Why does this happen? Why is open silicon becoming so prevalent in the world? And one answer is that open silicon can reduce reliance on existing closed tool chains. Another interesting aspect is that it's possible that open silicon may help to ease the impact of the current chip shortage by making it easier to select and switch foundations. It can also be chosen because if a country encourages local development of different cores, and not necessarily RISC-V, but their own processor cores, then that does potentially enhance national security because they're more in control of what goes into those cores and the specific needs for that jurisdiction. And therefore, they can also foster technological independence as well. And for the same reason, it's possible that the development of RISC-V and other open hardware cores can increase independence because, increase security, because it becomes much easier to examine the design of the cores as they are implemented and to ensure that no functionality within the core has been incorporated by somebody else, some bad actor, to make the cores do things that you do not want them to do. So there is the opportunity to increase security by scrutinizing the designs made available by open hardware as well. And as with open source software, it's also possible that open hardware can increase innovation by allowing innovation by allowing collaborative working using the tools that I mentioned before, like GitHub and GitLab. And it can also lower the barrier to entry for anyone who wants to get involved in the open hardware market by allowing smaller companies and even individuals and academic organizations to enter the whole open silicon ecosystem. So this is all exemplified and studied in some research that I was involved with the European Commission for a report that was published in 2021. So for the first time that I'm aware of, a country or transnational organization commissioned a report on not only open source software, but also open hardware as well. And one of the things that we did in this report is to distinguish between the hardness and the software of different types of hardware, softness of different types of hardware. And so the examples that I gave earlier is that an open source dump truck would be very hard hardware, and open silicon can be regarded as being very soft hardware. So the report noted that open hardware that is developed and available in a very soft way can benefit from the same sort of low friction effects as open source software. We also undertook some economic analysis for open source software, but we recognized that currently there is simply not enough data available to make any meaningful analysis as far as open source hardware is concerned. However, looking at the results as far as open source software is concerned, we noted that a 10% increase in contributions to open source software throughout the European Union could lead to a 0.4 to 0.6% increase in the GDP of the EU overall. So very significant impact for a relatively small amount of activity solely as regards open source software. And we made a number of recommendations which were applicable to open source hardware. So first of all, we recommended that the European Union implement a network of OSPOs, and that means an open source program office. So these are organizations within organizations that are tasked with understanding and monitoring and introducing and ensuring that correct regulation is applied as far as open source software is concerned, and we noted that the same type of organisations could be developed to also promote the use and regulation within organisations of open source hardware as well. We noted that it would be applicable to both open source software and open source hardware to increase funding and incentives within the European Union. And we also noted that increasing training and education around open source software and open hardware would be beneficial as well. We made some recommendations that were purely specific to open source hardware. So one of these relates to clarifying the liability regime for developers. At the moment, it's not entirely clear whether an individual in particular who is involved in developing open source hardware has direct liability to anyone who subsequently becomes injured, for example, by some failure of that open source hardware project. It seems that that's a potential inhibitor to people who would want to get involved in open source hardware projects. So we recommended that through legislation, the European Union clarified the position to make sure that individual developers in particular did not find themselves liable for particular issues with the designs that they were creating as well. We also recommended that standardization was increased around the area of open source hardware. And we recommended that patent law, copyright law, and competition law were also reviewed in the context of open source hardware as well. Now, one particular issue that we covered was an improved regulatory mechanism. At the moment, particularly in areas such as medical and automotive, it's quite difficult for open source hardware to be incorporated into designs because there are requirements around retaining dossiers of information, putting the hardware through certain tests, etc. These at the moment work much more effectively in circumstances where it's open, where proprietary designs are being used. So we recommended a change to the regulation to allow open source equivalents to be used instead, but at the same time to provide appropriate degrees of protection to the public and others. One extremely specific recommendation that we made was to standardize a bitstream format to reduce the reliance on existing electronic design automation tool vendors. At the moment, if you're making a design using one particular vendor's tools, it therefore becomes very difficult to switch that design to another vendor. So what we propose is to make this interoperability more straightforward and to make it easier for a particular design to be developed using a number of multiple vendors' tools to develop a standard for interoperability. And we would also hope that development of that standard would enable tools that were available under an open source license themselves to be made available rather than for designers, as they currently do, to be largely relying on proprietary tools. There are some open source tool chains starting to come into existence, but at the moment there really are not very many of them, and this is a situation which would be eased, as it is in open source software, by allowing more open source software tools like compilers, etc., to be produced. Thank you very much for listening. I provided some links to the various topics and organisations that I've been talking about, so feel free to follow those. If you have any questions at all, I'd be extremely happy to consider them. You have my email address, so please feel free to reach out at any time. Thank you again for listening. I do appreciate your time.